Imagine a data center delivering 4,000 peta operations per second. Now imagine it using just 1% of the power. This is the promise of optical systolic arrays, a groundbreaking technology by Neurophos Inc. Traditional silicon-based GPUs are hitting their limits in energy efficiency and cost. As AI demands more compute power, the energy consumption of these systems becomes unsustainable. Neurophos tackles this challenge with optical computing, focusing on energy efficiency first. Their approach reduces energy per operation by 100 times, minimizing environmental impact. AI performance hinges on compute density and manufacturing efficiency. Systolic arrays, a concept from the 1970s, revolutionized matrix operations for AI workloads. These arrays process data in a rhythmic flow, like blood through the heart. Digital systolic arrays are efficient, but plateau due to power consumption limits. Analog systolic arrays improve power efficiency by replacing digital elements with analog ones. However, analog implementations face signal propagation delays, limiting their speed. Neurophos overcomes these limitations with optical in-memory compute modules. Signals in these modules travel at the speed of light, eliminating RC delays. Optical arrays maintain analog scaling laws, but achieve higher efficiency as they grow. Previous attempts at silicon photonics failed due to large modulator sizes. Neurophos design features small modulators for massive arrays, enhancing speed and efficiency. Their optical systolic arrays are dense, analog, and photonic, offering speed of light propagation. These arrays are model agnostic and integrate with standard CMOS technologies. Neurophos's architecture efficiently handles large matrix multiplications, crucial for AI tasks. Their first-generation product processes massive matrices at 56 billion operations per second. Inspired by 1970s Fourier optics, Neurophos developed a compact module for vector matrix multiplication. Goodman's original concept used lenses and holographic films for multiplication and summation. Neurophos innovations include the world's densest spatial light modulator array. They also use optical folding to create a single-plane system architecture. Metasurfaces manipulate light wavefronts, acting as optical memories. Neurophos active metasurfaces can dynamically rewrite wavefront transfer functions. These metasurfaces are manufactured using standard silicon foundry materials. Switching speeds below 1 microsecond have been demonstrated, ensuring fast operation. Neurophos's metasurfaces offer advantages over traditional silicon photonic modulators. They are smaller, more robust, and avoid the extinction problem of crossbar architectures. Optical folding allows for compact and manufacturable modules, enhancing system efficiency. Neurophos first-generation product delivers 235 peta operations per second at peak efficiency. This efficiency is achieved while consuming significantly less power than traditional GPUs. Future developments aim to integrate even larger metasurface arrays for greater performance. Neurophos's innovations will help meet the growing demand for AI compute power sustainably. By focusing on energy efficiency, they align AI advancements with environmental goals. Neurophos's optical processing solution is pivotal in making AI compute abundant and accessible. As AI continues to evolve, Neurophos technology will play a crucial role in its sustainable growth. The future of AI is bright, with optical systolic arrays leading the charge towards efficiency.